So now when we talk about these concentration, we can look at concentration units. The first one that you were introduced to is molarity. We use the uppercase M, and this is molarity, and it means moles of solute per liter of solution, and you were introduced to this in Chem 111. Everybody remembers molarity? And do you remember that you have to write the uppercase M? It's not a big M because I could write a lowercase m really big. It has to be the uppercase, and we distinguish upper and lowercase, and uppercase M has points. This is a lowercase m. The lowercase m has humps, and it means molality, and that's something different. That is moles of solute per kilogram of solvent. One of them is about solution and one is about solvent. So they are different, and it's important that you distinguish very carefully how you write. We might talk about percent, and when we think of percent, it could be grams of solute per 100 grams of solution. That is percentage. We could have mole fraction. We use the uppercase letter X to represent the mole fraction. And that's equal to the moles of the part, whether it's the solute or the solvent, divided by the total moles of everything in the mixture. So there's lots of different concentration units that we can work on. Now, when we start to think about the dynamics of forming a solution, there are two factors. The first is the randomness. Mother Nature's tendency is for randomness and chaos to reign. So things will start to mix naturally when you pour them together. And the second thing we have to consider is the attraction that the solvent and the solute have for each other. Because in the liquid sense, these molecules are sitting next to each other. They're very close, so you have intermolecular attractions, whether it's London forces, also called van der Waal forces. Does that sound familiar to everybody? London forces or van der Waal forces? Okay, or dipole forces or hydrogen bonds. We have to break those attractions between the molecules and spread them apart and then let them mix in. So, solutions that are formed this way, we generally get an energy change, and we can think about this in terms of what has to go on for that solution to form. So when we have a liquid-liquid solution with two components, we have liquid A being poured into liquid B. The molecules of liquid B have to move apart in order for the molecules of liquid A to move in. For this to happen, the molecules have to be alike. We say that like dissolves like. And like or alike refers to polar versus nonpolar. Nonpolar solvents will dissolve nonpolar solutes. Polar solvents will dissolve polar solutes. Now, when we talk about this, we can think about things like ethanol and water. Ethanol, that's the alcohol in that whiskey we were talking about a minute ago. They're completely miscible because of the polar hydroxyl groups in these two molecules. So when we think back to Chem 111, we learned about water and making hydrogen bonds. That we have two molecules of water and we make these hydrogen bonds that are actually weak physical bonds between the two molecules. So we have to break those hydrogen bonds between the water and allow the ethanol to come in. So ethanol, what does eth mean? How many carbons? 2. Okay, so we have ethanol. And we have then water. So here's my ethanol, 2 carbons with an OH. Now I bring in a molecule of water, and what's going to happen? It's going to line up with the hydroxyl group on the ethanol so that we get this attraction. We can actually get hydrogen bonding between the ethanol and water again. So these things are all like, so they will be well miscible. Now, when we talk about some hydrocarbons, hexane and benzene don't dissolve in water, okay? Hexane, what does hex mean? 6 carbons, C6H14 hexane. This is a hydrocarbon, so it is nonpolar. Benzene, you probably don't know this one, it's C6H6. Benzene is a 6-carbon ring that has alternating double bonds. Now, we draw the structure with alternating double bonds. Does it really have alternating double bonds? No, what does it really have? Has what? Yeah, delocalized electrons, and there's a word that starts with R. What do we call that? Yeah, resonance structures. Students always want to call them Renaissance structures, but it's not. It's resonance structures. So we have the delocalized bonding. So it's not really double and singles. It's really something in between. Okay, it's delocalized bonding. So these things are very nonpolar, and they will be completely miscible. Okay, benzene, you might have heard of it because it is a component in gasoline, and benzene is an amazing organic solvent. When I was a student, we used a lot of benzene, and we would just reflux benzene for hours at a time in a laboratory with no ventilation and no hoods. And I can remember I was working doing a research project, and the guy I shared a lab with was refluxing flax seeds in benzene, and he'd have these benzene pots going for 10, 12 hours a day. We'd be in there and standing there and just kind of breathe it because it smells so nice. It's an aromatic. It's quite fragrant. And now they know that benzene is an inhalation hazard because it's a class 1 carcinogen. So that's a little bit disturbing for someone of my age and experience now to see that, all this time I spent breathing in a class 1 carcinogen. But obviously it's not affected me because I'm fine, right? You're asking me to do computer stuff. That is annoying. But if I move it too much, then I can't start and stop it. Put it up there. Now do what? You want me to do 2 things? Jeez. Anything else? You want me to dance or talk French or what? All right. Are we good now? All right, I'm going to stop this now because I've gone 8 minutes and that's too long.